Great to see you here. We are again at the last video of this fourth paragraph. We're talking about here the sequences and the summations. When we look at summations, why we do that? Well, we want to know what the summation of those sequences give as a result. And it's very important, very interesting to see, for example, what's happening with the value of those summations. When we look at the summation of a sequence, we consider, in fact, an addition. We add the different elements of the sequence. And we can write this when we have a sequence which is considered by the terms a index k plus 1 up to a index n. Then we can define the summation as, in fact, the sum of ak plus 1 plus up to an, which is equal to the summation sign of the a index I, the terms with index I, starting from I equal to k up to n. Now, the number I, or the letter I, is the index of the summation. And when we know the equation of the sequence, it's possible to find generalized summations that can be used for different sequences. And we have to look into the formulas to summarize these different elements. Let's first look at the summation of a geometric sequence. When we have a geometric sequence with the terms a and r, which both are real numbers, and r is different from 0, right? If r would be equal to 0, there would be no sequence. Everything would be equal to 0. We can say that the sum of the terms from 0 to n of the geometric sequence a times r to the power of I is equal to a times r to the power of n plus 1 minus a divided by r minus 1. And this is valued when r is not equal to 1. On the other hand, when r would be equal to 1, we can prove that the same sum is equal to n plus 1 multiplied by a. So these are the two possibilities that we have for the summation of geometric sequences. Now we can look at some other summations, some other summation formulas. We can look at the sum and the closed form. When we look at the sum of the integers, the positive integers I equal 1 to n, we find that the sum of them is n times n plus 1 divided by 2. This is also a very interesting sequence that we can consider. Another sequence is the sum of a sequence is the sum of all the elements of I to the power 2. Starting from 1, it's clear that starting from 0 has no sense, because then I to the square would be equal to 0. We can prove that this is equal to n times n plus 1 multiplied by 2n plus 1 divided by 6. And finally, we have a third power. These are the sequences containing I to a power. We have, in fact, n to the square times n plus 1 to the square divided by 4, which is in fact the sum for the powers of I, the third power of I, for I going from 1 till n. We have an infinite sequence from I going from 0 to infinity of x to the power of y. The absolute value of x is smaller than 1. And we can say, in this case, that the sum of this sequence is 1 divided by 1 minus x. We have another infinite sequence for I going from 0 to infinity. And here we have the term, the progression I times x to the power I minus 1. Again, for the absolute value of x smaller than 1, we can say this is equal to 1 divided by 1 minus x to the square. It is clear for the two last elements that the absolute value of x cannot be equal to 1, because then the denominator would be equal to 0, which is not acceptable. So this was the last element of this fourth paragraph, where we were talking about the summations. We are ready to go to the next paragraph, the fifth paragraph of this chapter, and here we will talk about the cardinality of sets. You're doing a great job. Looking forward to seeing you there. Thank you and bye-bye.